Hi everyone, and welcome to this episode of Keipert Labs in the dark room. I've switched the lights off because I'm working with my ray box again here today, looking at the behaviour of different mirrors and lenses. Okay, so just depending on whether these are things that you've seen or not seen, I figured I'd catalogue a few things so that you can then be able to understand them a bit better. So I'm using my ray box, and then I'm going to use a range of different flat and curved mirrors and lenses to talk you through the behaviour of light. Okay, so the first thing I'm going to do is I'm actually going to switch my light box to the 3 slits so that you can see the behaviour of multiple parallel rays as they look at these different objects. So the first one that we're going to look at is a plane mirror, a flat surface mirror, okay, just like the sort of thing that you'd have in your bathroom. Okay, so if I put that in front of my light box, I can see that it reflects my rays of light. Okay, you can see if I start to angle it, that you can see that I get these rays of light that hit this shiny surface and rebound in a predictable pattern, a predictable direction. Okay, and so depending on the angle that I put them at, they will reflect at a particular angle. Okay, we've looked at this idea of the law of reflection. Okay, that helps us to make predictions there. Okay, so simple kind of rebounding. All right, now what happens when we get a curved mirror? Okay, so if I get a curved mirror like this, okay, then I can position it relative to the light in 2 ways. This way or this way. Okay, so where it's curving, we would say that it is concave at the moment because relative to the light it's going in. Okay, so if I place this concave mirror in the path of my light, what I see is that I get reflections back towards the light box, but that they actually, it's a little hard to see with this contrast, but they actually meet together at a point around about here. Okay, if I kind of pinpoint it with a pencil, around about that spot, that those rays of light actually meet together. We say that they converge. Okay, so a concave mirror causes the light rays to converge or meet together at a particular point. Okay, this idea of them actually meeting together is the basis of the 3D structure of a satellite that is actually designed to capture rays of energy, whether it's visible light or something else, and focus them at a particular point where they can be detected. Okay, so the curvature of the satellite allows them to actually meet together at a specific spot. Okay, but now if I take this curved mirror and I position it the other way around, now what we would say is that this is now convex, okay, because it's curving. Yes, because it's bulging out towards the source of the light. And what you notice is that the light is reflecting off again because it's a mirror, but that our light rays are actually now spreading apart from each other. So there's some up here, down here, and then back towards the middle. You can see it a bit more clearly as I continue to change its orientation, change its direction. Okay, and so we call this a diverging mirror. So the light rays, rather than meeting together at the same point like we just saw, but they're now spreading apart from one another. Now, if I get another curved mirror which is slightly less curved, we can see that the curvature has an impact on what these light rays do. So I've now got a curved mirror which is slightly shallower, and you can see that curvature even better now. That it's actually you can see that converging point even better. Okay, so converging and diverging in a slightly different manner. Okay, and so depending on how curved it is, what we call the radius of curvature, that affects the distance away that we get to that converging point, which we call its focal point, where it's all focused together. Okay, so we've looked at plane mirrors and curved mirrors, whether they're curving towards or away from the light source, seeing how that affects its behaviour. Now let's have a look at prisms and lenses. Okay, so we've already had a look in the past, we've had a look at a rectangular prism when we've been looking at drawing ray diagrams. Okay, but so if I position it off to a bit of an angle relative to the light, rather than moving the light box, just this is going to be a bit easier for me to work with. Okay, but so we can see that as the light enters and then exits the prism, it is bent or refracted. So because this prism is made up of a different material than the air that it's passing through on here and on the other side, that we get a bending effect. Okay, so a perspex prism like this will have a different result to glass, which is different to water, which is different to air and a vacuum. So the speed and behaviour of light depends on the medium. It will travel more slowly through a denser medium, the perspex, than it does in air. But as it makes the transition from one medium to another, it changes direction slightly. So you can see that I've got 3 parallel rays of light coming out this side, which are slightly offset from where they are over here. They line up, but not directly. Okay? Now, so that's a rectangular prism. What about if I look at lenses? Okay, so first of all, I'm going to show you what's called a biconcave lens. So this biconcave lens, so it curves in towards the center of the lens on both sides, hence the bi in its name. Okay, so it's curving on both sides. Okay, so now if I put that lens in the path of those three rays of light, you can see that they spread apart from each other. Okay, so that we have one that's kind of passing through the middle more or less as it was. Okay, if I get the right, it should be fairly unobstructed. Okay, but then the ones on the edge are bending away from each other. So they've been refracted because of the curving of that lens, and they've bent, and so they don't focus together. Okay, so a biconcave lens is often also known as a diverging or divergent lens because it causes the light rays to spread apart from each other. Okay, so now what about if we take the opposite type of lens, which is called a biconvex lens? Okay, so I've got two shapes here that I'm going to show you before I start putting them in the path of the light. One is a thick one and one is a thin one. So biconvex means that they curve out from the center. So if this is the center, that it curves out on both sides, so it's biconvex. Okay, but so we have a thin one, so it curves out not as much, and then this one curves out significantly more. Okay, so if I start with the thin one here, what you notice is that rather than making the light rays diverge, that this type of lens makes them converge at this point here. Okay, so this is what, as I mentioned before, the term is the focal point. And what we can do is that we can also say, all right, well, we can measure the distance from the focal point to the center of the lens and in centimeters, and they'll actually determine, express that as a distance value. Now watch what happens when I put a thicker lens. Okay, so you notice that it's also making it converge, but you see how the distance is much shorter. Okay, the thicker the lens is, the shorter the focal length, or that is the closer this focal point is to the center of the lens to start with. Okay, so what we have there is we now have it's a fairly simple kind of relationship. Like we haven't really done anything mathematical, but just seeing that the thicker the lens was, the closer the focal point, and that is the shorter the focal length. Okay, now the last thing that I'm just going to show you, just to kind of round things off, I'm going to show you a triangular prism. Okay, so a triangular prism, which looks like this. Okay, I'm going to place it in the middle here. And what we can see is because of the multiple angles going on in a triangular prism, that we can cause the light to be split in lots of different ways. So at the moment, this kind of lines up like an arrow, and so I'm getting this splitting happening in both directions here. Okay, but depending on how I rotate it, I can get those light rays to do all sorts of funky things, which is why it's pretty clever and pretty cool. Okay, now, you probably can't really see it very clearly, but actually what I have in these rays over here are actually a rainbow of color. Okay, now you might be able to see it a bit better if I take the slit card out. Okay, the contrast is still, it's a little bit bright. Let's see if I can bring that down. Okay, so you can see a colored band over here. Let's see if I can, it works a little bit better with glass than it does with perspex. Just trying to have a play. It's a bit hard to get it to do what I want right now. Okay, but so this idea that we can actually, because of the positioning of the prism, we can actually split up the light into its component colors. The light that we would call white is actually made up of multiple different colors. Okay, and so there you go. So we've looked at the different shapes of mirrors, the different shapes of lenses, and some of the behavior that we see there. There you go. All right, thanks very much for watching. Bye for now.